Great. So I was assigned the task of doing non-SUSY physics at the LHC. And if you stop and think about that for a minute, that's a very broad topic. So I took this as carte blanche to talk about whatever I think is most interesting. So this set of 2 lectures is going to be about generic physics beyond the standard model that is not SUSY. And I want to motivate this by this overarching principle that has really driven all of particle physics, all of high-energy particle physics for the last 3 decades. And that, of course, is naturalness. So naturalness is this notion that you have a Higgs mass sitting around the weak scale, around 100 GeV. If you calculate quantum corrections to the Higgs mass, you expect it to be much heavier, and so you feel driven to find some type of mechanism that will cancel off those divergences for the Higgs. So let me just give you sort of an outline of where we're going to go. So I want to remind you of these naturalness arguments in the context of SUSY and ask, is naturalness really just a natural addiction? Okay? And I think the reason why the urgency of this question, I mean, it's certainly been a question that's been around, I think, since the LEP program. But the reason why it's getting even more and more urgent, of course, is because we're pushing up the scale of new physics at the LHC. And, of course, we're still not seeing anything. So the question is, why might that be? So I want to review these naturalness arguments within the context of supersymmetry, which you've already heard about, as I understand, from Natalia Toro last week, but we'll review it then also within the context of little Higgs. So we'll talk about SUSY and little Higgs, okay? Then what I really want to spend the lion's share of these 3 hours that we have together on looking beyond naturalness. So we've been really focused on looking for new physics that solves the hierarchy problem. And if we're going to move beyond looking for new physics that solves the hierarchy problem, what is it that we should use as our organizing principle? Okay. And I want to talk about really 2. What should we use as a guiding principle? Well, let's talk about 2. One could just be to be agnostic. And this sort of goes under the question of how to be ready for anything. We have a multi-billion-dollar machine, and the searches that are currently being implemented are focused on looking for solutions to the hierarchy problem. If that's not the place we should be looking for new physics, where should we be looking for it? So I want to spend some time talking about basically signature-based theories at the LHC. The other thing that I think is a really strong guiding principle is dark matter. The fact that we know that it exists and that we have an argument from the WIMP miracle for why we might expect dark matter to be at the electroweak scale. So as you know, if you calculate the number density of dark matter from freeze-out, and you do this freeze-out calculation where it drops The annihilation drops out of thermal equilibrium when the annihilation rate drops below the Hubble expansion. And then you measure this from, now it's going to be Planck plus large-scale structure. Then what you get is an annihilation cross-section is somewhere on 1 on a TeV squared. And this is a reason why people took dark matter as a strong motivation by itself to look for new physics at the electroweak scale. Now, of course, it may be the case that there are other reasons, there are other mechanisms for setting the dark matter mass. I mean, axions are one example of that. But at the same time, this is a good reason to expect that it might be there. Now, in most cases, in supersymmetry, for example, dark matter is embedded within a larger structure. And you go and look primarily, actually, for the colored particles that appear in those theories. But you could take a different philosophy and just say it's electroweak interacting dark matter. Take a minimal dark matter type philosophy. Okay? So here are two. And then the third one that I'm going to say, and looks like I may need to pick up top board. Is that we've discovered the Higgs. Looks like a standard model Higgs. We sort of presume and think it is a standard model Higgs, but of course we don't know. And it's awfully easy to modify the properties of the Higgs with new physics. So these are the three things that we're going to talk about as organizing principles for looking for new physics, which is not obsessed with this naturalness question. Okay, so this is where we're going to be going over the next couple of hours today and tomorrow. All right. Questions, comments, problems? Okay. All right, so let's just start with this naturalness, okay? And just to make sure that we're all on the same page, let's talk about, great way to start off, is to look at it in the context of SUSY, which you've heard some lectures about. Okay, so let me just review this. We know that the limits on sparticles is that squarks and gluinos have masses somewhat above the TeV. Limits are stronger for the gluinos than for the squarks, but sort of order of magnitude, you know, they're sitting up around a couple TeV for gluino and around 1 TeV for the squarks. And the reason why this is getting to be an increased problem with naturalness is because, on the one hand, the Z mass is set by this relation between the mu parameter and the mass for the up-type Higgs. And if these superpartners are too heavy, then these two parameters have to be tuned against each other in order to actually realize the physical Higgs mass. Okay, so if they're heavy, this implies a tuning. Okay, so that's on the one hand. It's incidentally also the reason why you expect Higgsinos to be fairly light. Yes?
Is it possible for neutrino to be one of the organizing principles?
For a neutrino?
Yeah,
It is possible for a neutrino to be an organizing principle. Usually the argument that people make about neutrinos is that if you take an EV neutrino, and I take the Dirac mass to be around the weak scale, then that would imply the scale in new physics would be quite heavy. Of course, it doesn't have to be that way. I just think that these three are stronger links to potential modifications at the weak scale. I'm not claiming to be exhaustive. I'm giving 3 examples, and certainly you can take it as a challenge to think of as many other types of non-SUSY physics or non-naturalness motivated physics at the weak scale as you want. But certainly I'm not being exhaustive, yeah. Okay. So if these guys are heavy, then that would seem to imply some type of tuning. Now if we define a tuning parameter to say that if I'm adding in some type of correction to the Higgs over the actual observed Higgs mass, that if I compare these two against each other, we say this parameter is large and hence highly tuned if these corrections are large in comparison to the mass of the particle that's observed. Okay, this makes sense as sort of an intuitive reach. Okay, so we know that corrections to the Higgs from, for example, stop loops is minus 3 on 8 pi squared. You have a top Yukawa, and then you have the soft masses sitting in there. And then it's log enhanced, okay? So taking this definition then for the tuning, what you find is that if you want a natural theory at sort of the 20% fine-tuned level, then these particles need to be fairly light. Okay? So already pushing up the constraints on the stops above a TeV is already telling you that SUSY is sort of tuned at the 10% level. So you may or may not be bothered by that. Clearly it's a much less badly fine-tuned problem than just allowing the radiative corrections of the Higgs to be pushed up all the way to the Planck scale. But nevertheless, if your goal of this theory is to actually make the Higgs mass itself natural, then this concerns you some. And in fact, I don't think that this is the worst problem. We sort of already knew that particles shouldn't really show up at a very low scale, and the reason for that is before something shows up as a real emission, you know, some particle that you're really producing, you actually expect to see it in loops. And we've measured the standard model very, very well through precision electroweak. And so as a result, through precision electroweak and also through flavors. So for example, you can induce contributions to KK bar mixing. This is actually the strongest constraint. And depending on what the operator is, if these particles are quite low, you would expect this would give rise to large corrections to KK bar mixing. And in fact, the fact that this is in agreement with the standard model actually puts very stringent constraints on the scale of this operator. It's 980 TeV is the number. You get an even stronger constraint if you look at this operator instead. That actually corresponds to about 18,000 TeV. Okay. Now, people have devised things to try to fix these flavor problems. One, for example, is gauge mediation. However, at the same time, gauge mediation actually has some difficulty in producing a Higgs mass that's as heavy as 125 GeV. Now, people have introduced other mechanisms for trying to push the mass of the Higgs up within gauge mediation. But at some point, of course, you do start to wonder, well, why haven't I seen any sign of new physics in any types, in sort of a generic way that you would expect from a theory which solves the hierarchy problem. And it's the combined direct measurements, not having seen those particles, along with these sort of indirect measurements that I think are putting us in that direction. So now you can say, well, so maybe SUSY isn't in totally awesome shape. I mean, it's certainly not dead. We're certainly going to keep looking for SUSY at the LHC. Maybe composite models are better. The strongly coupled models, whether that be Technicolor or RS or composite Higgs models. And Raman talked some about those last week. And those, in many ways, suffer from the same types of tuning problems. Okay, now, they're sort of at the 10% level of GAN, similar to SUSY. So let's take as our example 2 as little Higgs. Now, little Higgs works by extending the SU2 to an SU3, and then actually breaking that SU3 twice by 2 fields. And the pseudo-Goldstone bosons of this breaking from SU3 to SU2, I'm just giving it a simple example, there are other gauge groups that you can use, is the Higgs. So for example, okay, this is actually a 3 column vector. Okay. So I'm going to break it. I'm going to break this SU3 to SU2 with both of these fields. Okay, I'm taking F1 is equal to F2 for convenience. I don't necessarily have to do that. But just to keep things simple, I'm going to do that. And I can reparameterize this thing as in the following way. And phi 2 as the identical thing. But with a minus sign sitting in the Higgs piece. So here, again, shorthand, there's a 2 by 2 matrix up here. So the Higgs is going to be a 2-component complex field sitting here. And so when you calculate, now using this parameterization, when you calculate the divergences, so you write down a Lagrangian, which is d mu phi 1 plus d mu phi 2, okay? And calculate the quadratic divergences for these scalar fields here, phi 1 and phi 2, from the SU3 gauge bosons. What you find is that the quadratic divergence looks like g squared on 16 pi squared, lambda squared, phi 1 dagger, phi 1, plus phi 2 dagger, phi 2. And that, of course, only depends on f squared. In particular, the Goldstone bosons don't get quadratic divergences. Okay, and the reason for this is actually that what you need to get a divergence for the Higgs is to write down a diagram that looks like a combination of both phi 1 and phi 2. So if I write down a diagram that instead looks like this, Then I get a divergence, but the divergence for phi 1 dagger phi 2 is only logarithmic and not quadratic. So if you calculate this diagram, this thing goes like g to the 4th on 16 pi squared log lambda squared on mu squared phi 1 dagger phi 2 mod squared. And this, in fact, is actually where you get the mass term for the Higgs. So the mass term for the Higgs in these little Higgs theories goes like g to the 4th on 16 pi squared log lambda squared on mu squared f squared. And that is the thing that has to be on the order of the weak mass squared. And so what that tells you then is just putting in the electroweak coupling constant here, that this scale f is on the order of a TeV. Okay. Now, that's fine, except that you have to take a look at the contribution from the top partners themselves. So now I've extended SU2 to include SU3, and so the top sector then needs to be extended accordingly. And so you can write down then the fermion sector has to include the top, the bottom, and the top partner, and then there are right-handed fields to go with that. And the Yukawa sector then just looks like lambda 1 phi 1 dagger psi T1 conjugate. So where T1 is just going to be some linear combination of little t and big T. And likewise for phi 2. Okay. So now taking the choice, so again, just to make things simpler, I'm going to take lambda 1 equals lambda 2. You can work out the general case of what it is if lambda 1 does not equal lambda 2. Just plugging in these expressions for the scalar fields and these fields, then what you find is that the Yukawa couplings become the following. Okay, where I've made the definition that T conjugate is equal to T1 conjugate plus T2 conjugate divided by square root 2. Okay, and likewise that this little t conjugate is equal to T1 conjugate minus T2 conjugate, again with the square root 2. Okay. Now, the reason why that's relevant is that you see that it's the same coupling constant here that's giving both the top Yukawa, which is sitting here, as well as the Yukawa coupling for these top partners. And so what that's telling you is, since we know that the scale f has to be around a TeV in order to actually generate the mass term, what that tells you is that the natural mass scale for these top partners is about a TeV as well. So already, even without doing a search, you see that the naturalness problem is not 100% solved. You sort of naturally, again, end up with order 10% fine-tuning. So let me take these SUSY ones down. And having those top partners around a TeV actually implies then that you'll induce corrections to the Higgs. So those Yukawa couplings are going to give rise to diagrams which look like this. Or this is, again, the Higgs. And these quadratic divergences cancel up to the scale of this mass. And again, since that's sitting around a TeV, you end up inducing about 10% fine-tuning. Okay. Now, there are things that you can do to sort of weaken those constraints somewhat. At the same time, both ATLAS and CMS experiments have done searches for these top partners, predominantly in these modes. And the constraints that you get out of these, sort of back of the envelope level, is that this top partner has to be heavier than something around 800 GeV. So both from naturalness point of view and just what the natural scale that the theory wants for these top partners, you again need sort of 10% fine-tuning. Okay? Now, there are certainly many people who think that 10% fine-tuning is not a problem. We should just keep pushing on and pushing, further and further. But certainly that's a fixed part of the LHC program that needs to be pushed to the very end as far as the collider energies are going to allow us. At the same time, I do think that as we move further and further along, natural theories are going to become more and more unnatural. I think if you just look at the structure of these theories, having to add more and more sort of moving parts to them to make them function the way they should, that's maybe indicating that we should think about physics beyond the standard model, which is not simply constructed for the purpose of canceling quadratic divergences of the Higgs. Okay? So that's the motivation for the rest of this talk, that we have a 10 billion plus machine with thousands of creative experimentalists looking for many different types of new physics, and we should try to optimize this as best as we can. So before I go on to talking about that, are there any questions about this section? So I think pieces of this you've heard in other lectures that people have given so far. I just wanted to review it for completeness. Okay? All right. So we're either happy or unhappy, maybe unhappy because we haven't found new physics yet at the LHC. So what should be the leading principle? Well, so I want to start by talking about A, being agnostic. So we know that we're inherently limited by machine energies. We're not going to magically be able to push ourselves up to the Planck scale. But once we produce a heavy state, the only thing that we can actually see, of course, is its decay products. And so if the decay products are in some type of unusual form, the reality is that there are cases where we may not see them. Now, I think for the most part, experimentalists have made a pretty good case that they'll trigger. If you can build a trigger for something, it's already there. I think they've made a pretty good case for that. On the other hand, analyses are usually tuned to new physics models. So they're tuned to doing a supersymmetry search, or they're tuned to doing a search for a top partner, or they're tuned to looking for some type of resonance. So we filled out the case where you have some heavy new states. So examples of this would be, for example, you could just add some new z prime. May not be motivated by anything in particular. It could go to a pair of muons, or it could go to a top pair, which would be very well motivated, for example, in RS types of theories. And the constraints on both of these are that the mass of this resonance depends on the details of the theory, of course, but it's somewhere around TeV, give or take plus or minus a TeV. Okay? And you can also look in dijets. Again, depends on the details of the theory, but again, you get a constraint around a couple of TeV. You can look for a fourth generation. This is dead by the impacts that it would have on the, for example, gamma gamma. Okay. So, and there's also been direct searches for fourth generation. There's also strong constraints on a fourth generation from the S&T parameters. You can look for, I'm just at this moment giving just kind of a list, and I'll tell you in a minute why I'm giving you this list. Could look for leptoquarks. So pair produce some states which decay to a lepton and a jet. And these appear in more models than you might expect. So they've done searches for second and third, so decaying to a muon and a jet, or decaying to a tau and a top. And the constraints on these, also not trivial. CMS did searches where they put constraints on these. For a second generation, this was with 8 TeV data. With 7 TeV, it was this was 7 TeV full data set, and this was 8 TeV. Okay, marching along. You can look for a color octet. Okay, you pair produce or singly produce some gluon, which then decays maybe to a pair of jets, or else you can pair produce that state, which each decays to a pair of jets. You can look for paired dijet resonances, or for this one would be constrained by the standard dijet search. So this paired dijet kills things between 300 and 800 GeV. Okay. So why am I going through this list? I could probably keep going on about the types of objects that they've constrained at the LHC. The thing that you should notice that they all have in common is that you're looking for heavy states which are decaying to very energetic standard model particles, typically with not very high multiplicities. And in fact, you can see explicitly from this search that the constraint dies off when you actually get to a low enough mass resonance. And the reason for that, of course, is you get buried in standard model backgrounds. So what you're doing at the end of the day is basically making cuts on hard objects to reduce the standard model backgrounds and to look for all these exotic types of states. So bottom line, the lighter and the softer the states, the more the LHC tends to struggle. So can anyone give me an example of a classic case where the LHC struggles with actually closing the window because the decay products are just too soft? Digets? It's true, yeah. Any others? Of course, in that case, you have lower energy machines. So there you can take advantage of UA1, UA2, Tevatron, and you can close some of those windows. That's definitely true. Any others? Any other takers? What? The Higgs. That's true. You have to dig it out of the background. That's why at the end of the day you take advantage of gamma-gamma, because it helps you to reduce the background. Good. Let's keep going. Anyone? SUSY, yeah. Hidden sectors? Yep, that's what we're going to talk about more in detail. Good, you're getting ahead of me. Any others? Compressed spectrum, exactly. Okay, so this was a specific example I was going to give, is that, so for example, let's take pair production of a chargino with a neutralino. Okay, so there are two different ways that this can decay. So we can produce neutralino 2 and a chargino, which decays to a lepton, spit off a lepton, go to another lepton and a neutralino. And likewise, on the other side, I hope you guys can see that. You'll get a charged lepton and a neutralino. Okay, so you look for the 3 leptons, and if you look at the constraint, say from this particular search, so for this set of decay modes, you'll have, let's look at the mass, take a common mass of the neutralino 2 and the chargino, just for simplicity, and look at the mass of the neutralino, and take 100. So this dashed line here is going to be the region where it's absolutely compressed, where the mass of this guy is degenerate with the mass of this guy. And what you usually see is that there's a region here that they just don't have any reach. You can have very, very light charginos, and you just would not be able to pick up these objects simply because the decay products, now they're able to go out to about 600 GeV in the chargino mass. Okay, not as good of reach here in the neutralino. Okay, so I'm looking at, this was an Atlas search. Try lepton. Search. Okay, but there's this entire compressed region here where they, even though they were actually trying to close that window as much as possible, they just didn't have any reach. Simply because if you have a lepton that's softer than about 25 GeV, life gets much, much harder. You're also going to be struggling with diboson backgrounds in this region. Likewise, you can look at the case where you're pair producing the neutralino and chargino. And then in that case, you decay through off-shell Z, for example, which will go through a pair of leptons. And in this case, the constraints are actually weaker because you take a branching fraction hit from the W to the leptons. But once again, you still have the problem that much of this parameter space you just cannot touch simply because the decay products are too soft. So in this case, you could have, again, a neutralino and even charginos that are not much heavier than 100 GeV, and you still wouldn't be able to pick them up simply because the leptons in the decay are not that hard. So you're suffering both from the fact that your production cross-sections aren't that big because they're electroweak only, so you don't get the advantage of having the strong production cross-sections, and the fact that when it actually decays, the leptons that you produce in the decay aren't actually that hard. So it's hard to beat back the standard model backgrounds. So the basic problem then is that you're balancing falling backgrounds, usually 1 on S hat backgrounds, against the signal rate. And so the way that you beat this, of course, with, say, a Z prime search is that you take advantage usually of resonant production. So what you're usually doing is looking at rates, say in femtobarns, and you're comparing a rate, say, let's take WW, or I guess this would be a Z. You can also look at WW, and in the center of mass, of course, you're going to get the giant Z peak. And WW, of course, you get this broad distribution out to fairly high energies. But for these heavy resonance searches, of course, it's easy because, relatively easy, because basically what you do is you just wait, go to high enough energy and wait for that state to peak out as you go to higher and higher energies, and these guys gradually just die. And of course, really what you're running into, what's killing the constraints here is just that you have these huge weak backgrounds, just diboson production, for example. Okay. So the strategy then is to make hard cuts on jets, on leptons in order to kill the background. And then, of course, the thing that you worry about is that in the process of doing this, you're actually missing a lot of new physics simply because all the new physics is buried in these events. And so you want to ask the question, well, what kinds of models are going to give rise to these kinds of physics? And then further, once I've written down these models, can I use unique handles in these searches to try to pull them out from the backgrounds that are sitting there? And of course, this is an ongoing discussion. There was just a paper on the archive today, in fact, about ways that you could try to close this window by using soft leptons, but then triggering on a hard jet. At the end of the day, you still need some type of hard object in order to do that. Okay. So going along with this agnostic focus, to this point, you've sort of been focused on, let's call it a trifecta, okay, of new physics. Okay. Strong dynamics. Okay, so this we'll put little Higgs in this, RS, Technicolor, which has died due to the discovery of the Higgs. Okay, you can put SUSY up there, and here you can just put new heavy resonances, maybe not directly motivated by these, but which they're pretty efficient at looking for. Okay, this is not what we're going to talk about. Okay, I want to talk about dynamics in a hidden sector for the next while that in many ways is related to this type of dynamics but would be missed because these searches are really focused on using hard objects, okay? So we're going to talk about, in place of the strong dynamics, maybe I need a new board. In place of the strong dynamics, we're going to talk about hidden sector strong dynamics. That is not directly associated with the hierarchy problem, but which may be there and may show up, but would not be looked for. And these go hidden strong dynamics. So examples of these would be hidden valleys, quarks, and unparticles. Okay. So up here I want to talk about supersymmetric hidden sectors. In particular in the context of dark matter models. Okay, you can have dark matter with mass well below a TeV, which is supersymmetric, and in some cases would be difficult to discover at the LHC with the current constraints. Okay. And then the last one I want to talk about is exotic Higgs decays, okay, which is a resonance we've actually discovered. All right, so those are going to be the basic topic. And when I say hidden sector dynamics, what I basically mean by that, so a hidden sector is going to be defined as light states which carry no standard model charge. Okay. And in addition to the hidden sector, then, if we're going to have any hope of seeing it at the LHC, what do I need in addition to the hidden sector particles? What? Yes, a mediator. We need some type of connector sector. And this connector sector, of course, they have to be charged under both hidden and standard model. Okay? And both of these will have obvious applications both to the Higgs, because in this case, the Higgs can actually be a very efficient connector sector to a hidden sector. It's not hard to modify the Higgs decay at all. And going to have obvious applications to dark matter because, in fact, the dark matter may reside in this low-mass hidden sector. And I'll give examples of models where this is well motivated. Okay. And I should also comment that this has the virtue that if we're focusing on applications to Higgs physics and dark matter, I think these are two of the areas that are making the most experimental progress right now. In part because both are known to exist. questions, comments? All right, so structure then that I'll be talking about is then to draw a picture, which is really valid for any hidden sector theories. That I have the standard model sector, I have the hidden sector, and of course I need some type of barrier between the two. Okay? Otherwise it wouldn't be hidden. Okay? And this type of barrier can have two types of barriers. They either go under energy or intensity. Okay? So this barrier could be an energy barrier because this is a massive resonance. In which case you need a high energy machine, say the LHC, to catapult yourself up to produce this resonance. Now once you produce this resonance, it can have the boring decay back to the standard model, which is the case we usually focus on. On the other hand, it can have more exotic decays into a hidden sector. And the structure in this sector, of course, is completely unknown. Okay, not completely unknown actually, because cosmology puts a lot of constraints usually on these sectors. But nevertheless, the types of signatures that you might get could be much more varied than what you might get from just decaying directly back to the standard model. So that's the energy. In the case of intensity, you have standard model, you have hidden. You no longer have this heavy resonance that's decaying back to the standard model or into the hidden sector, but instead what I might have is a weakly coupled light state. Okay, so one very popular example in recent years of this has been to use kinetic mixing between hypercharge and a dark photon. And if this kinetic mixing is pretty small, this dark photon doesn't need to be very heavy, but I simply don't produce it very often just because it has a relatively small coupling to the standard model. And in that case, I really need an experiment where I'm just producing a lot of, in some cases, relatively low mass states in order to be able to actually tunnel over into this hidden sector. Okay? So I should maybe just write this explicitly that this connector in this massive case might be a Higgs, it might be a Z prime, it might be new heavy quarks. There are examples of all types in the literature that you can write down. Okay. All right, so I'm going to start with the case of the Higgs, because that has been, of course, the news of the last few years is the discovery of the Higgs. And let's look at why the Higgs might be a good connector. So the Higgs width is small. So if I just look at the ratio of the total width to the mass of the Higgs, that's going to scale something like the U-Powell coupling to the bottom quark divided by 16 pi or something like that. So this is, something that's on the order of 10 to the minus 6. So the Higgs is a very, very narrow particle, simply because the states that it's most strongly coupled to, like the tops and the SU2 gauge bosons, it can't decay to on shell. So the thing that it can decay to on shell, it doesn't have a very large coupling to, and as a consequence, the width is very small. And so from a new physics point of view, it's really easy to modify Higgs physics. You don't need new physics that has very strong coupling to the Higgs in order to give substantial modifications to the Higgs branching. At the same time, the total width of the Higgs, so for example, if you want to put a constraint on the invisible width of the Higgs, that is also not very strong. Anyone know what that constraint is off the top of their head? Invisible width of the Higgs. It's about 20%. Okay? Someone was shaking his head. Is it bigger than 20%? It's like 60%. I thought it was 50% with last year's data, but it could be that it's still large. Yeah, it's like 60%, unless you make very specific model-dependent assumptions. Okay, all right. So in any case, it's order 1. So if it's order 1, constraint on the total width, then, and that's just on the invisible width, okay, then there are a lot of things that you can do to it that you can go out and look for. And in fact, there are some existing searches. You can have Higgs goes to invisible plus a dark photon. I'm just going to describe some of the existing searches. Okay. And most of the time when they do this, they pick out particular regions. So in this case, if you look for 400 MeV dark photon, gamma prime, then the constraint, and you look for displaced vertices, and we'll talk about in a minute why you might expect displaced vertices in these decays. The limit on this lifetime, so if I take a 1 to 10 centimeters, so this is a displaced vertex, 1 to 10 centimeters, the constraint on this branching fraction is about 1% for this particular choice. The mass, if you go very far away from that, the constraints will start to change. If you go far away from this mass or this lifetime, does anyone want the archive numbers of these searches? Anyone interested in looking them up? If so, I can certainly give them to you later. Just to give you an idea of some of the things that the collaborations are doing right now. In associated production, I can have Higgs decaying to 2 pseudoscalars. Pseudoscalars can decay to dark photons. Those can go to E plus E minus. And same thing on this side, so I would have a large number of electrons. So they looked at, again, a very specific mass range. They didn't require displaced vertices in this case, but also not very strong constraints on the branching fraction. Okay. And the reason, I'm just going to go through a bunch of topologies, and the reason is I'm using it to motivate a particular class of models we'll look at. You can look at Higgs going to 2 pseudoscalars again, which goes to 4 photons. You can look at Higgs going to 2 pseudoscalars, which goes to 4 muons. And the constraints on these, again, not very strong over particular, although in some regions of parameter space you can get pretty strong constraints. Okay. So a couple of questions then for this might be, well, why might you do this? What theories might give you light pseudoscalars with displaced vertices with sort of modest branching fractions of the Higgs to these exotic states in comparison to the B quark. So let's just write down a simple model where this happens. Let's just take the NMSSM with the pseudoscalar, a singlet pseudoscalar. Okay, and let's take a superpotential in this case, an example. Singlet extended Higgs sector. You wouldn't have to write down a supersymmetric model. I could easily write down a non-supersymmetric version of this model. But let's just take an example. As B goes to 0, I have an x goes to minus x symmetry. And that stabilizes x. So if I had Higgs going to 2 of these particles, that goes like lambda kappa v over yb mh mod squared, which, because again, this guy is pretty small, these don't have to be particularly large in order to actually induce a substantial branching fraction of the Higgs to these states. Then once you've decayed to these states, by taking a term that x is going to go to heavy flavor via a loop, and that loop is going to come from taking the potential term here, so I can have x mixing to s through the off-diagonal piece, and that mixing goes like kappa b on 16 pi squared. So if this singlet is heavy, okay, and these couplings are fairly small, then I can still have a substantial branching fraction of the Higgs into this hidden sector by controlling these parameters here, But the lifetime then of the particles that the Higgs has decayed to can be fairly long just by taking this parameter to 0. Okay, so it's not hard to construct simple toy models where this type of behavior arises. Okay. And in fact, there was an atlas search for this type of model, producing the Higgs to pseudoscalars to BB bar with extremely displaced lifetimes. The mass of this pseudoscalar being fairly high, and the branching fraction, the constraint from this search was something between 0.1 and 3, depending on what exactly the decay length was. Okay. Okay, so let me give you an example. This was a weakly coupled model where this happened. So let's take a look at a strongly coupled model. So let's take, for example, pair producing, so the Higgs. Then the Higgs is going to decay to now 2 fermions. These are light fermions. And these fermions then are going to be strongly coupled under some gauge group, which is sitting in the hidden sector. And then we're going to get some hadronization. Okay, so let's just take the simplest case where I produce then through this process the decay to 2 dark pions. Okay, it's taking, for example, so let's suppose I have, looking at the Higgs, plus 2 dark quarks. Okay, these carry no standard model charges. But these dark quarks are charged under a hidden SUN. Okay? This is actually not strongly constrained by anything. You're adding a lot of new matter to the standard model, but it's not constrained by cosmology, except for these few searches that I've described done by Atlas and CMS, not directly constrained by the collider searches up to these sort of order 1 branching fractions. Okay, and what could happen then is these guys then might mix back with some new mediator, let's say it's a Z prime, and then they'll decay to standard model particles. Now that's just the simplest case. Things can get much more complicated than that. In fact, I might produce 2 of these dark quarks. Then, depending on what the structure of the mass of the dark quarks versus the confinement scale of the dark SUN, I can actually produce many of these resonances. So for example, I can produce a dark pion which has the up isospin. This is not electric charge. This is an isospin quantum number that I'm writing down here. If I have two flavors, I'm going to have 3 of those states. I'm just going to give plus, minus, and 0. Okay, so of course you can produce multiple other states, and then these things will propagate out. And these guys will decay to BB bar, but the ones that are plus and minus, to conserve the flavor symmetry, these are actually stable. So these escape as missing energy. So now I have the Higgs decaying to a few of these dark resonances that I've gotten by adding to the standard model gauge group 2 dark quarks plus a hidden SUN. Okay, so this is even a structure that's simpler than the standard model, not constrained by cosmology, not constrained by the LHC. In fact, these states here might be good dark matter candidates. Okay. And, so this is just one example. I can also have an example where I would just have one light dark quark. So phenomenology would be somewhat similar. I wouldn't have a dark matter candidate in that case because I wouldn't have a flavor symmetry to stabilize. But I would still get this hadronization in the dark matter sector, and then these states would then decay. I would maybe get the analog of a sigma or an eta or an omega. I would get the entire zoo, but again, these guys would decay to combinations of standard model particles. And the fact is, because I've produced a heavy state, so I have a lot of energy available from the resonant production of that state. But once it decays, I've got a lot, if these states are light, I've got a lot of phase space for producing a lot of these particles. And so what you end up with is high multiplicity low mass resonances. And this is, in fact, exactly what the exotic Higgs searches were targeted for at the LHC. So before I stop today, I want to flesh out this model in a little more detail so you can see a little bit better how it might work and why, again, in this case, you might expect long lifetimes for these particles. So let's take an example of the two-flavor model. So we're going to take 2 light, dark quarks, pun intended. Okay. And the reason why you might do that, just as an example, is you can use QCD as an analog with the up and down quarks. And so you're going to write that as U and D. And the confined degrees of freedom are dark pions. Okay. So we're going to call these things, I'm just going to put a superscript on to denote that they're dark states. And just write out what the charges of these particles are, just to be totally explicit. We'll define the mediator particles to be the Z prime and the Higgs. Okay. And so in that case, you can write out the explicit charges. So this is for the heavy state, the Z prime, and then there's going to be a dark SUN. Okay. So let me actually change the name of these guys because this is poor notation. Call them V1 and V2. These are the dark quarks. Okay. And I can just write out a table with the quantum numbers of these states, and then the scalar sector. So this is the standard model Higgs, and then there's a Higgs in the dark sector as well. Okay? And of course, these are all singlets under standard model quantum numbers. Just keep writing singlets. Okay? But in this case now, the Higgs is going to be charged under this new U1, and the dark quarks now are going to be charged under this dark SUN. They're going to be fundamentals. Okay. And these quarks are also going to pick up charges under this dark U1. And I'm going to be careful about canceling anomalies. And in order to actually give a mass to these particles, I'm going to require Q plus Q minus to be minus 2 in order to actually fix the mass of these states. Now what happens in this model now is once I produce a dark pion, say this state, this guy is actually going to mix through this state and decay via the Z prime. Because it's a pseudoscalar, it'll prefer to decay to the heaviest flavor available. If it's above twice the B mass, it'll go to two B quarks. Otherwise, whatever is the heaviest mass lepton that's available. Okay. So you can compute the lifetime of this dark pion that I've gotten from a construction that's not totally trivial, but is still simpler than the standard model and is still totally consistent with cosmology. And I can compute the lifetime for this, and it looks like the following. So as you would expect, the lifetime is going to go like 1 on the Z prime mass to the 4th. This is the gauge boson associated with this gauged U1, and this is the coupling constant. Then there are the charges here, because in order to decay through the Z prime, I'm actually mixing this guy with the Higgs, with the dark Higgs and the visible Higgs. So these charges appear on both sides. Then there is the dark decay constant, analogous with standard model. And then the term that comes from the mixing with the Z. And now I need to sum over all the flavors that are available. And again, as with standard model pions, I'm going to be suppressed by the chirality by putting in a mask insertion for the final state lepton. Okay. So here's an explicit model, and now you can just put in numbers for this explicit model for the lifetime of these particles to decay to the heaviest state available. And if you put in those numbers, what you get out is that the lifetime of this dark pion is very long, potentially. Long enough that you may see macroscopically displaced vertices at the LHC. Okay. So here's an example of a hidden sector where I've added additional structure of a dark confining gauge group with 2 additional quarks where the lifetime is such that you expect displaced vertices at the LHC, where I have substantial branching fractions of the Higgs into these dark states via mixing with this state. And for only a limited region of the parameter space would the current searches currently constrain this model. Okay. So this is one type of physics that is not standard, which the collaborations are have several analyses devoted to, which is consistent. If you still want to hold on to all the notions of naturalness that you have, is still consistent with all those notions, but would give rise to a dark matter candidate in the form of these dark pions. Okay? And nevertheless, could still escape detection. So I'm going to stop there for now because I want to launch into talking about related classes of hidden sector theories. And that discussion would continue for a while. Are there any questions about this? Yeah. No, the Z prime actually gets a mass from this Higgs. Yeah.
And the mixing is, can you elaborate on the mixing? Z prime exists?
Yeah, so the mixing is going to come from an h squared phi squared type of term. So I'll have some term in my Lagrangian which is going to go like kappa h mod squared phi squared. So when both the Higgs and the dark Higgs pick up VEVs, then that mixing will induce a decay of the ordinary Higgs into the dark sector. Other questions? Yeah.
In terms of the Higgs couplings to dark photons,
Mm-hmm.
how does one write down a Lagrangian term which gives you that coupling, which is sort of SU2L invariant?
Yeah, so it's going to come from the Higgs here is going to mix with this scalar, and then that scalar has a coupling to a pair of these quarks. And that's what allows for the decay of the Higgs into the hidden sector. And again, because the Higgs couplings to standard model fields, you know, the branching, the total width to BB bar is small. That mixing doesn't have to be very big, and I can still have a substantial branching fraction of the Higgs into these dark states. Yeah. Yep.
So also the gate, how do you trigger on these things?
How do you trigger on these things? Right, so So there was a search that was actually done. It depends on the particular search. I can certainly give you archive numbers for the searches that have been done by both ATLAS and CMS. And a number of these, they actually use the displaced, they don't trigger on the displaced vertices, but you still have fairly hard B quarks, for example, in these events. So if you require, say, if you require several B tags, for example, then in principle, so for example, in this type of search, where they had this displaced vertex, they had the pseudoscalar was between 20 and 40 GeV, and then they just required heavy flavor, several heavy flavor tags that they could tag and use that. And in that sense, it's not very much different from the Higgs to PB bar search itself. Same type of kinematics. It's just that we have 4 in this case, and there's a displaced vertex as well. Other questions? So tomorrow I'm going to pick up talking about 2 related classes of models where either the confinement scale, where the mediator particles are heavy, I don't have any light quarks, and instead you pick up these exotic oscillating types of tracks. They're called Quark models. And I'm going to talk about the relation to unparticles, and then pick up then pushing this third one, which is the connection of these hidden sectors with dark matter and with the stability of the electroweak vacuum. So I will stop there.